Welcome back to geometry. We just introduced the idea of spherical geometry, our first non-Euclidean geometry, and we looked at the example of it on the ball. So let's take a look at what our notes have to say about some of the results in spherical geometry. So one of the things that we discussed was that the shortest distance between 2 points in any geometry essentially is called a geodesic. So the path of shortest distance is always called a geodesic. And on a sphere, those are arcs, right? Those are the things that are traveling along in space. This rubber band is traveling on a circle, but in fact, if we just look at a part of it, it would just be an arc. So geodesics are arcs that lie on the circle. But because they split the sphere in half, these are actually called great circles, which are circles whose radius, okay, if you think of it as a circle in in three dimensions. So we have just the flat circle, but its radius is the same as that of the sphere. Okay. So these are of course, the largest circles we can make. So examples are good examples are the equator, and let's see here. Equator is a good example of a great circle, and lines of longitude are also good examples of arcs, pieces of a great circle. Okay, so if we think of this, then the model that we took a look at on our ball, then our model consists of the points R, right, the plane. The points that compose the plane are the points on the surface of the sphere, and then the lines are the great circles, and the distance is just the distance along the shortest arc, right? Because if I have 2 points on that great circle, I want to choose the shorter of the 2 distances, okay, right? Because I could go a long way around or the short way. Of course, the short way is the distance. Yep. Okay. And then angles, if we were to consider, we have to think almost in a calculus 3 way here. But if we were to consider the tangents, okay, so here we have a curve, and if we take the tangent to the curve at this point, the point of intersection, and we take the tangent to the curve, maybe I'll stop and share here a second. Tangent to the curve, tangent to the curve, that gives us our angle. Okay, the angle between the tangents. So that gives us the ability to talk about angles, distance, lines, points, and yes, excellent. So the incidence postulate. 2 lines will always meet. We already talked about that. And because of that, the incidence postulate fails. Okay, so when we talk about the incidence postulate, what we're talking about is, if I remember correctly, that we're talking about there being a line between any 2 points, and that line being unique. In this case, in the case of a sphere, if we take 2 points which are on opposite sides of the circle, then, or if you think of the North Pole and South Pole, right, they're opposite sides, then every line of longitude passes through the North Pole and South Pole. And if you were to just continue on that line, right, and yeah, well, there's an infinite number of them. So there's an infinite number of lines between 2 points which are opposite one another on the sphere. And points that have that characteristic are called antipodal points. I've also heard it pronounced antipodal, or maybe that's just me making fun of the way the word is spelled. I don't remember anymore, but antipodal, I believe, is the correct pronunciation. So the incidence postulate fails. All right, there are no parallels. No parallels. We already showed that. Right? 2 great circles will always intersect. Great circles are the lines. Okay, if you consider a circle that's not a great circle, that's simply a circle on our geometry here. So any two distinct great circles will intersect at a pair of points. Those points are antipodal points. Thus, for one result is parallelograms do not exist. If there's no parallel lines, we can't have a parallelogram. So that's kind of interesting. All right, so what else? Well, the furthest away 2 points can be is antipodal points, right? As soon as if I travel along a great circle, the furthest I can travel before I start getting closer to where I started is actually halfway around the sphere, okay? So the furthest distance I can go from something is however far halfway around the sphere is. So there is a bound on the distance between points. So specifically for points P and Q, PQ is less than, well, how do you determine the distance halfway around a circle? Well, pi times r, 2 pi r is the circumference, half their circumference is pi r, where r is the radius of the sphere. So PQ is equal to pi r, right? They obtain that maximum distance apart if and only if the points are antipodal. Excellent, right? They're on opposite sides of the sphere. So we already also saw that the sum of the angle measures in all triangles is more than 180 degrees. We saw this in the previous video. And then we also took a look at the exterior angle sum, or the exterior angle theorem in the last video as well, which we found to be false. So just as a nice reminder, if we were to take that sphere, and if we thought of the equator, or the Earth rather, and the equator, and then we looked at a line of longitude and another line of longitude. All right, we've created a triangle here where the sum of the interior angles is more than 180 degrees. And if we can notice that angle 1 is equal to the angle measure of the measure of angle 2. So measure of angle 1 is equal to the measure of angle 2. But in the exterior angle theorem, it states that we have the exterior angle theorem wants us to have that the measure of angle 1 is greater than the measure of angle 2. Okay. That's what the exterior angle theorem would say. But what we have in reality for spherical geometry is that the angles are equal in this particular example. So there might be other places where it's in fact greater to, and there may not be, but the point is we found a spot where it's equal to, so the exterior angle theorem is false. All right, so the area of a triangle is proportional to the difference between its angle sum and 180 degrees. So as we talked about earlier, when we looked at the smaller triangle, it had an area that was closer to 180 degrees. So then, of course, if we have a larger area, we're saying that it would be a larger difference from 180 degrees for the interior angle measure sum. So again, we already essentially discussed that. But that's it essentially for spherical geometry. There's a nice comment that you can read here as well, and I would encourage you to do that. But I think that gives us the right idea for spherical geometry. And that's all that I have to share with you for that. We want to return again and take a look at hyperbolic geometry. which we don't quite have the nice visual representation for. There are a few different models that we can use, but they're not not hands-on like this. So thank you for your time and attention, and I will see you guys again soon.